Welcome to this presentation. Today I'll explain our recent work, anomaly detection using state space models and reinforcement learning. My name is Shervin and I'm the co-author of this paper that is published recently in the Journal of Structural Control and Health Monitoring. In today's presentation, I'll start off by our motivation to carry out this research. Then I'll present the nature of the anomalies and how to quantify them so we can detect these anomalies using reinforcement learning. In section 4, I'll explain and support the framework by showing you a real-world case study. And in section 5, I'll show you how to quantify the detectability of the trained agents. And finally, I'll wrap up the presentation by highlighting the main conclusions of this work. So without further ado, let's begin. In infrastructure monitoring, we use sensors to record structural responses and surrounding environmental effects. For example, these two time series show an example of the collected data on a bridge in Canada. On top, you see the elongation data of the span obtained from an extensometer over the period of 6 years. The horizontal axis is the time and the vertical axis shows the measurements in millimeter. On the bottom, you see the air temperature data around the bridge within the same 6 years. And also, the shaded area is related to the year 2011 that we know that there was an intervention on the bridge. As you can see that not only the elongation measurements consist in its own pattern, but also it is affected by the temperature data. Based on our previous work, now we are able to infer the measurements data using Bayesian dynamic linear models, which is a particular case of the state space models. BDLM has two main objectives. First, it removes the external effects and decomposes the structural responses to reveal the underlying dynamics, which we can call them hidden states. The first three figures from the top show the underlying dynamics or kinematics of the responses. They are the baseline or local level, baseline rate of change or speed or local trend, and the speed rate of the change or local acceleration. As you can see, each hidden state is inferred by the mean mu and the standard deviation sigma. The black line is the mean values and the shaded green area is the corresponding to the plus minus 1 standard deviation. The second objective of the BDLM is to identify the regimes, which is a dynamic model describing the evolution of the local level, local trend, and sometimes local acceleration over time. If you look at the speed or local trend figure on the second figure, you notice that we can identify two different regimes. For one of them, the trend is locally constant, and for the other one, it is not. And when we don't have the locally constant trend, of course, we're going to have acceleration. Because take a look at the fourth figure, and it shows the probability of changing between these regimes that trend is not constant. So basically, the fourth figure is the probability of the non-stationary regime. Okay, so for the year 2011, when we know that there was an intervention, the probability is 1 and it is considered an anomaly. But how about the other time steps where the probability is not 1, not 0, but somewhere between 0 and 1? Should we consider them as an anomalies and, let's say, trigger an alarm, or should we just ignore them? And this is our motivation. How do we make decisions for such situations? Of course, this motivation brings some challenges that eventually lead us to some opportunities to carry out this research. Okay, let's see what are the challenges. We have basically two challenges. First, what is the notion of the anomaly? In another word, what is the nature of the anomaly? Also, how do we model anomalies, especially considering the fact that they are rare events? And the second challenge is, how do we make decisions? For example, trigger an alarm when an anomaly happens. But at the same time, we don't want to have a lot of false alarms or miss an anomaly. And we want to know what is the long-term effect of our decisions. So the next sections, we're going to address all of these challenges and you will see a real-world example. Okay, first let's define the notion of the anomaly. Consider a time series data as shown on the left figure. Let's assume that the composition of the data leads to the shown mean values of the underlying dynamics, as you can see on the right side. As you can see, we can identify two regimes, stationary and non-stationary. The two regimes are shown by the check mark and the warning sign. The stationary regime follows a constant speed, while during the non-stationary regime we expect a non-constant speed or acceleration. The mean values of the baseline, speed, and acceleration clearly show the difference in the regimes. We can define the notion of the anomaly as a transition between these two regimes. In other words, the notion of the anomaly is when the dynamic switches between the trend or constant, locally constant trend and the acceleration and vice versa. And our objective is to make decisions in the form of triggering an alarm when these switches happens. So to do so, we need to be able to quantify such transition mathematically. Let's quantify the anomaly function with respect to the local trend or speed. Okay, consider the anomaly function f of a as a function of the time and some stochastic characteristics. The function should be bounded according to the length of the time series between t1 and tt. Such a bound is shown in the figure by dashed lines. Also, we need a function that is differentiable because we consider the anomaly function as a change in the speed, yet the effect can be seen on the baseline and accelerations, which are the derivative and the integral of the speed. Okay, so what we did, we chose the logistic function as a general form of the anomaly function, which is differentiable and unbounded and symmetrical with respect to the center of the function, which we call it t of c or t of center. The general form of the function is going to be a division, which on the numerator we have h of max, and on the denominator we have e plus e to the minus k multiplied by t minus tc. And the maximum height is h of max, and you can see that the t of c is the time on the center of the anomaly, and k is the steepness. Now, let's define the stochastic characteristics of the function such that they have engineering meanings. From the figure, you can identify the start and end of the anomaly for a given anomaly width A. So basically, we can write the anomaly width in terms of the beginning and the end of the anomaly. In fact, WA represents the non-stationary regimes, and the function is colored in the red lines during this period. The epsilon a is the error due to the start and end of the anomaly, and therefore the actual height of the anomaly is a bit less than the maximum height of the function and can be easily calculated. Last but not the least, by doing some math, we can obtain the expression for the steepness as a function of the anomaly height and anomaly width. And so, using these new expressions, we can write the anomaly function as a function of these stochastic characteristics, which are anomaly center, anomaly height, and anomaly width. And here I provided the functions and the steepness, and also this set, which I call it by J, is the center, the height, and the width of the anomaly. Now, once we have this function, we can create realizations from these random variables, and each of these realizations lead to a new anomaly that can be easily evaluated for speed, baseline, and acceleration. Now let's illustrate the anomaly simulation. For example, let's consider that the center of the anomaly is a random date sampled from a uniform distribution between the years 2010 and 2011. The anomaly width, or non-stationary period, is a random number days sampled from a uniform distribution between 60 and 80 days. So this is basically the value of the anomaly width that we want to sample from this uniform distribution. And finally, the height of the anomaly is sampled from a uniform distribution between 10 to the minus 5 and 2 10 to the minus 3, and the unit is millimeter per day, or whatever unit that you have based on your measurement. So a realization from this distribution results in an anomaly that the center is on the July 2nd, 2010 with 63 days width and 0.0015 unit per day height. And the figure shows the resulting anomaly with respect to the baseline, speed, and acceleration. And again, this function is on the trend or on the speed. So by doing like an integration and derivation, we can obtain the baseline or the acceleration. And also the shaded area is the anomaly width, and the vertical line indicates the center of the anomaly. Okay, the figure shows some realizations of the anomalies and corresponding time series that we can generate by adding the anomalies on top of the simulation data that we obtained from the BDLM. The red line is the real time series, and the black lines show the simulated time series. The vertical dash line that you can see here shows the number of days without the anomaly. So we assume that, for example, for the first, let's say, 50 days, we don't expect any anomalies from the beginning of the time series. Okay, and if we keep going, once we created this simulated time series using BDLM, we can obtain the underlying dynamics and the probability of non-stationary regimes using the same model dynamics that we use for the BDLM. So the figure shows the resulting mean trend and the probability of non-stationary regime. The yellow areas are the anomaly width, and the vertical dashed lines are the center of the anomalies. As you can see, BDLM sometimes identifies the anomalies with high probability, and sometimes the probabilities are not high. Therefore, only using BDLM for decision making regarding the presence of the anomaly can result in many false or missed alarms. In addition, we still don't know about the long-term effect of the decision. For example, at a certain time, before deciding whether we are facing an anomaly, it might be better to wait and postpone our decision to make sure that we prevent the false alarm. So the decision-making challenges led us to use reinforcement learning to use its capacity to consider the long-term effects of the decisions while minimizing the number of false alarms. Let's see how the reinforcement learning works. Let's take a game of the Super Mario as an example. The objective of the Mario or the agent is to find the best action using the joystick inside the game environment. The environment has obstacles, mushrooms, and bonuses. At each time step, what you want to do is to use the joystick to make the action and move around the environment. And in return, the environment gives you some rewards. And you will be in the next state, or in this case, the position in the game. At the same time, when you are playing the game, you want to consider long-term effects of such that you can maximize the current and future rewards. For example, you might want to use the joystick to jump earlier so you can pass the obstacle and get the bonus at the same time. We can formulate our anomaly detection problem in the same fashion. Instead of the game emulator, we can use the BDLM environment. So instead of mushrooms and obstacles, we can use the probability of regime switching and the mean value of the speed. Instead of the joystick to move around, we can define our own actions, for example, do nothing or trigger an alarm. And finally, we can use our own reward function and let the agent to maximize the rewards considering the long-term effects. So let's go through the concept of reinforcement learning in more formal ways. Okay, first let's take a look at the BDLM environment as shown on the right graph. In this work, we use the mean value of the trend and the probability of non-stationary regime as our environment. It includes different time series that we call each of them an episode. The figure shows sampled episodes both as time series on the left and the BDLM environment on the right. Now let's formalize the environment. Here, the BDLM environment is a two-dimensional space that includes episodes like the one shown by the blue line or the dashed lines. At any time t, the agent can be in the state S of t, which consists in the trend and the probability of non-stationary regime. Therefore, an episode is a collection of these states. For each episode, the anomaly starts at time t of s, t of starts, and it ends at time t, t of e. The reward is a function of the state and the action and it is basically the action that the agent can take. It is a scalar value indicating whether the action was good or not. I will talk about this reward in a moment. And as I mentioned before, the action can be trigger an alarm or do nothing. Therefore, the agent-environment interaction can be defined as, at state t, the agent takes the action a of t, and it collects the corresponding reward and moves to the next state. And the objective of the agent that is to collect the maximum of the notion of the rewards over all the episodes by taking proper actions. So there are many algos to perform such maximization, and in this work we use the Q-learning approach. Okay, the last piece of information is to define our rewards. Here we use a reward function based on the confusion matrix. And the table shows the reward terminology depending on the agent action, that you can see it on the left column, at any time, and the optimal action that should be taken. So based on this confusion matrix, we have 4 different values. For the FP, or the false positive, which are corresponding to the time steps that are outside of the non-stationary regime area, and that the agent is going to trigger the alarm when it shouldn't trigger the alarm. The true negatives are related to the situations that the agent correctly taking the action of do nothing, which it indicates by the R, TP, TN, or true negatives. The false negative is related to the situation when the agent should trigger the alarm, but it doesn't. And finally, the true positive, or the TP, is to correctly trigger the alarm within the non-stationary area. So let's wrap up this work in the form of a single generic framework that is applicable in real-world problems. Okay, as you can see, the framework includes the 3 stages. In the first stage, we build an empirical model to estimate the underlying dynamics of the structural responses along with the probability of non-stationary regimes. In the second stage, we use the anomaly function to generate new anomalous time series and the subsequent underlying dynamics, and then we use it as the environment for the third stage. And in this third stage, the last stage, we use the reinforcement learning to train the agent to detect the anomalies. Okay, let's see an application of this framework in detecting the anomalies on the same data collected on the bridge that I showed to you in the beginning of this presentation. Okay, the 3 figures on the left show the results of our training and the post-processing. Figure A shows the results obtained from the Q-learning in a discretized environment. And then each cell within this figure represents a small region of the agent state. The horizontal axis is the mean trend, and the vertical axis is the probability of non-stationary regime. The colors are the policy of the agent, or the actions should be taken for each state. The red color represents taking the action of triggering the alarm, and the blue color indicates taking the action of do nothing. And the white color represents the states that aren't visited by the agent. We smoothed the policy map in the figure A with a mean filter of size 5 by 1, and you can see the results in figure B. And finally, we use the k nearest neighbor, in this case k equals to 10, to extrapolate for the non-visited states. So for any time series at any time t, we need to find the state of the agent on the policy map, and according to this color we can see the optimal action. Okay, we tested the policy map on the real time series data collected on the bridge. The top figure is the mean trend, and the bottom one is the probability of non-stationary regime. And the shaded area is corresponding to the time when there was an intervention on the bridge. The red dots on the figure shows that the agent triggered the alarm. And for the rest of the time steps, the action is do nothing. As you can see, the agent correctly identified the anomalous time steps associated with the intervention. And interestingly, the agent identified an anomaly for the time steps during the year 2009 when the probability is less than 1. And however, for the time steps during 2007, the agent did not trigger the alarm. This is a real application of the RL incorporating underlying dynamics in decision making. Now let's examine the robustness of the proposed method for some artificial anomalies. So here, what we did, we introduced two different anomalies on the time series, as you can see on the top left figure. On the left, you can see the anomaly function and the location of the anomalies on the time series. And on the right, you can see the agent policy that is triggering alarms for the anomalous parts that we introduced, along with the anomalous timestamps that was corresponding to the intervention. So up to now, we have an agent that can detect the anomalies. But how can we quantify the detectability of the agent? In the following section, I'll show you our proposed method to quantify the detectability of the agent. Okay, before proposing the metrics to quantify the detectability, let's review the terminology of the two main types of detection. In this work, we define a true positive detection when the agent triggers an alarm at time t after the start of the non-stationary regime. And the false positive is then defined when the agent triggers the alarm before the non-stationary regime starts. Given these two definitions, we introduce two metrics: the probability of true positive detection and the annual false positive ratio. Let's see how these two metrics works. The probability of true positive is quantified with respect to two parameters: n, the number of months after the beginning of the anomaly that the agent triggers the alarm, and the second parameter is the height of the anomaly. We tested the agent on 3000 time series, and the figure shows the results. The horizontal axis is the anomaly height in millimeter per year, and the vertical axis is the number of months after the beginning of the anomaly that the agent triggered the alarm. Here, the red dots in the figure shows the points of the trigger, considering that the agent keep triggering the alarm after the first triggers. The blue dots show the points that the agent didn't trigger the alarm. So here we can use the GPC or Gaussian process classification to carry out the binary classification to create the boundary decisions. The figure shows the results of the GPC and the decision boundaries for triggering the alarm. Any point on the graph indicates the probability of triggering the alarm with respect to the anomaly height. The two artificial anomalies we introduced earlier are shown by the circle and the diamond marks. For the current agent, the probability of detecting such anomalies is around 40%. Okay, the second metric is the annual false positive ratio that easily can be calculated by counting the number of the false positive over all time steps in the test set. We use a test set of 3000 episodes without anomaly to count the number of false positives. And it turned out that the agent has the ratio of 0.1 anomaly per year, which it means that the agent gives one false positive every 10 years. So up to now, we have established a framework to detect the anomalies and quantify the detectability of the agent. Now let's examine different agents' behavior. Okay, we can change the agent's behavior by changing the reward values. The figure shows the policy maps for different agents with different reward values. Figure A, B, and C are associated with the agents that have an equal true positive reward, but the false positive rewards are different. So we assigned more penalty for the agent A and started to reduce this penalty for the next agents. As you can see, the agents with higher penalty value is more conservative, such that for small values of the trend, it requires to have more probability of non-stationary regime in order to trigger the alarm. This can be seen easily by comparing the blue area in the figures. On the other hand, for the agents D, E, and F, we kept the penalty corresponding to the false positive to be equal and started to increase the reward for the true positives. And as you can see, the agents become more aggressive in the sense that for the same trend value, the agent triggers the alarm with low probability corresponding to a non-stationary regime. And note that the figure D is the agent 4 that we use in this work. And agent 5 and 6, the last two agents, are the agents that they trigger alarms always, even for the small value of the trends. Okay, let's look at the detectability from another perspective. We want to see how many months will it take for the agent to detect anomalies with 50% probability. So the figures on the left shows the number of months required for the agent to trigger the alarm anomalies with like 0.5 millimeter per year anomaly with the probability of 50%. And the right figure is a comparison of the 50% probability of true positive and the annual false positive ratio. We can see that as the agent triggers alarm earlier, it is at the cost of an increase in false positive ratio. So choosing the agent is up to our expectations that to what degree we can accept the false positive ratio. And on the side note, agents 5 and 6 are inadmissible as they trigger the alarm all the time. And here, the illustration of them is just for the sake of the comparison. Okay, let's wrap up what we have done in this paper. So in this work, we proposed an anomaly detection that introduce a framework that it combines the ability of the BDLM to decompose the time series with the long-term decision-making capacity of the reinforcement learning. In addition, we proposed a formalism for anomaly as the transition between the stationary and non-stationary regimes, and we showed that the application of the framework on the real data collected on the bridge. And later, we propose a method to quantify the detectability of the anomaly detection framework. And finally, we compared different agents' behavior and showed that how the detection metrics varies depending on the selection of the reward function values. And in the end, we would like to thank PJCCI for supporting this work. And if you have any question or comment regarding this work, please do not hesitate to contact us.